All right, everyone, welcome. So, if you've ever been in a stats class and thought, simple random sampling just doesn't feel like it captures the real world, well, you are in exactly the right place. Today, we're getting into the nitty gritty. We're moving beyond that textbook ideal and diving straight into Chapter 7, an introduction to complex surveys. This is where we get the tools to handle the messy, structured, real world populations we actually need to measure. So, let's just jump right in.
So here's our game plan for today. We're going to start with the basics. What even are complex surveys? Then we'll get into the fun stuff, the core building blocks of how you design them. After that, we'll see how these ideas work in the real world with a case study on malaria in the Gambia. From there, we'll unpack the power of sampling weights, and then we'll wrap up by talking about a really critical trade-off, simplicity versus complexity in survey design.
Okay, so let's start with the big picture. Why do we even need to bother with complex surveys in the first place? Well, the fundamental challenge is trying to understand a whole population. Think a city, an entire country, or a very specific group of people when it's just impossible, or at least crazy impractical, to talk to every single person.
This right here, this is the question. This is what drives the whole field of survey sampling. Now, a simple random sample, it's a beautiful thing in theory. But in the real world, populations have structure, right? They're spread out geographically, they have social groups, and there are all kinds of logistical headaches. So, to get a picture that's accurate, efficient, and doesn't break the bank, we need a much more sophisticated toolkit. And that's exactly what complex survey design is all about.
All right, let's pop open that toolkit. These next three concepts we're going to cover are really the fundamental building blocks of almost any complex survey you'll ever see. We're talking cluster sampling, stratification, and ratio estimation. You can think of them like the primary colors of survey design. Once you master these, you can pretty much create any sampling picture you need. First up, cluster sampling. So instead of trying to make a list of every single person in a country, which, good luck with that, it's often impossible, we can make a list of, say, every city block or every school. Those are our clusters. We then randomly pick a sample of those clusters, and then we go in and survey everyone, or maybe a subsample of everyone, inside them. It's an incredibly practical approach that saves a ton of time and money, especially when your population is spread all over the place. Now, let's get into the math a little bit, because this stuff really matters. On the left, you've got sampling with replacement. This is the one that's a bit simpler mathematically. Our estimator for the total, that t-hat, is basically a weighted average of the cluster totals. Here, Tij is the total for a cluster, and psi is its selection probability. So we're just weighting each cluster total by the inverse of its chance of being picked. The variance formula probably looks familiar. It's a lot like the standard error of a mean. Now, on the right is what we usually do in practice, sampling without replacement, using what's called the Horvitz-Thompson estimator, t-hat. Here, pi is the inclusion probability. What's the chance that cluster I makes it into our sample at all? The variance is way more complicated because we have to account for the fact that picking one cluster changes the probability of picking another.
Next up in our toolkit, stratification. The big idea here is to chop up your population into subgroups, or strata, that are really similar on the inside. So for example, you might stratify a state into urban, suburban, and rural areas. Then you sample independently from each of those groups. And what's the goal? To slash the overall variance of your estimate. By making sure you get good representation from each key subgroup, you actually remove the variability between those strata from your final calculation. And that often leads to a much more precise estimate.
And this is the mathematical beauty of stratification. Look how clean this is. To get your overall estimate for the population total, t-hat, you literally just add up the estimates from each stratum, t-hat. And because you sampled independently in each one, the math for the variance is just as simple. The total variance, v-hat of t-hat, is just the sum of the variances from each individual stratum. This is so powerful. It means you can be strategic, maybe sample more heavily in a really variable stratum to really control the precision of your final number.
Okay, our third tool is ratio estimation. Now, this one is a really clever technique you can use when you've got some extra information lying around. So imagine you want to estimate the total number of hospital beds, let's call that Y, in a state. You do a survey of hospitals to get an estimate. But what if you also happen to know the exact total number of hospitals, let's call that X, from some official government registry? Well, if the number of beds is strongly correlated with the number of hospitals, you can use that known total, Tx, to adjust and seriously improve your estimate for Y.
Let's just walk through the logic here. It's pretty cool. First, you use your sample to get estimates for both your main variable, Ty, and that extra variable, Tx.
The ratio of those two gives you B. That's your estimated ratio. So in our example, it's the average number of beds per hospital in your sample. Then, and this is the magic step, you take that sample ratio, B, and you multiply it by the known population total of your extra variable, Tx. And boom, that gives you TYR, your new improved ratio estimate for the total number of beds. You're basically correcting your sample's finding based on some known ground truth information.
Now here's the key. In the real world, we don't just use one of these tools, we combine them. Real surveys are multi-stage. And this formula might look a little scary at first, but it's really just us putting our pieces together. See that outer summation, the one from H equals 1 to H? That's our stratification. We're just summing across our strata. And the inner part, sigma JNSH THI over pi HI, well, that's just our Horvitz-Thompson estimator for clustering. But now we're just calculating it within each stratum H. So all we're doing here is running a cluster sample inside each strata and then adding up the results. This is a classic bread and butter complex survey design.
Okay, theory is great, but let's see how this all snaps together in the real world. We're going to take a look at a survey from 1991 on the use of insecticide-treated bed nets in the Gambia. This case study is just a fantastic example of a multi-stage, stratified, clustered survey design that was used to answer a really critical public health question.
So the objective here was crystal clear, and it was vital. Malaria is a massive problem, and these treated bed nets are a huge intervention. But for the whole strategy to work, public health officials had to know, are people actually using them? They had to estimate how widespread their use was across the entire rural population to figure out if their health policies were working. So how'd they do it? They used this brilliant 3-stage design that perfectly combines all our building blocks. Okay, stage 1 was clustering. They picked 4 districts from each of the 3 major geographic regions. But see, those regions themselves acted as a first layer of stratification. Then, stage 2 was stratified clustering. Within each district they picked, they chose 4 villages, but first they split them into 2 groups, those with a health clinic and those without. Finally, stage 3 was just simple random sampling. They randomly chose 6 compounds, basically homes, from each of the villages they had selected. This whole multi-stage approach is what made a nationwide survey logistically even possible.
This table just lays it out so perfectly. At stage 1, you see the stratification variable was the geographic region, and the sampling units are clusters, or districts. Then at stage 2, the stratification was based on whether a village had a primary healthcare clinic, and the sampling units were the villages themselves. And finally, stage 3, no more stratification. They just did a simple random sample of the compounds inside each village. You can see how the designers just cleverly wove together stratification and clustering at these different stages to make sure they got good representation, while keeping the fieldwork totally manageable.
Okay, so we've got our sample, it's complex, it's multi-stage. Now what? How do we actually calculate our estimates, the prevalence of bed net use? The answer is all about sampling weights. This is the engine, it's the mechanism that lets us take our complicated sample and use it to say something valid about the entire population.
This formula looks super simple, but it is the absolute core of everything. To estimate a population total, T hat, we just take a weighted sum. We go through every single unit, I, in our sample, we take its value, yi, like how many bed nets it has, and we multiply it by its sampling weight, wi. That weight, it basically tells us how many units in the whole population this one little sampled unit represents. And because of our design, some people in our sample will represent way more people than others. So where do these weights even come from? Well, in the simplest case, like a stratified sample, the weight for some person J in stratum H is just NH divided by NH. That's it. It's the total number of people in the population for that stratum divided by how many people we sampled from it. It's literally the inverse of the selection probability. Think about it. If you sample 100 people from a stratum that has 1,000 people, each person's chance of being picked is 100 over 1,000, or 1 in 10. So their weight is the inverse, 10. Each person you talk to represents 10 people in the population.
Okay, but for a multi-stage design, like our Gambia example, the weights get multiplied together. The final weight for a household is the product of the weights from each stage of sampling. You'd calculate the weight for its district, WI, and then you multiply that by the weight for its village within that district, WJ/I. Every stage of selection adds another layer to that final calculation.
And this formula just shows the full picture for that 3-stage Gambia survey. The final weight W for any sampled household is the product of 3 different parts. You've got the district's weight, WP, times the village's conditional weight, WS by P, times the compound's conditional weight,
WT by SP. It's this final weight that perfectly corrects for that whole chain of events that led the survey team to that specific household's front door.
So this brings us to a really critical point about sampling weights. They're absolutely essential, but they do not tell you the whole story. The weights have all the information you need to calculate your main number, your point estimate, like a total or a mean. But, and please remember this, the weights alone tell you nothing about the variance. To calculate your standard errors, your confidence intervals, you need the full design information. You need to know the strata, you need to know the clusters that were used. That underlying structure is what actually determines the real variability of your estimate.
And the fact that we need more than just the weights to figure out our variance kinda hints at a deeper issue here. We've spent this whole time looking at all these complex tools that give us statistical power and efficiency. But all that complexity, it comes at a cost. And that leads to this fundamental trade-off that every single survey designer has to wrestle with. This is such a powerful piece of wisdom. Why? Well, because simpler designs are just easier to actually pull off in the field, which means less chance of human error. And, maybe even more importantly, they are easier to analyze correctly. A really complex design might be perfect on paper, mathematically optimal, but if it's so complicated that the next person who gets the data can't figure out how to properly calculate the variance, then all those theoretical benefits are just lost. Practicality and clarity often win out over pure mathematical efficiency.
And so, I'm going to leave you with this question to kind of chew on as you move forward in your careers. The tools of complex survey design are incredibly powerful. They let us answer questions we could never answer otherwise. But you don't use them just for the sake of it. Your job as a statistician isn't just to build the most efficient model, but to build the most effective one that's robust, practical, and that people can actually understand. Finding that perfect balance, that line between necessary complexity and elegant simplicity, that's the real art of survey design.